Welcome to Biochemistry Simplified. Today, we explore one of the most fundamental topics in biochemistry, amino acids, the building blocks of life. From their structure to their essential roles in protein synthesis and metabolism, we'll break it all down in a simple and easy to understand way. If you're new here, make sure to subscribe for more simplified science content. Now, let's get started.
Hello, welcome to Biochemistry Simplified. Welcome to our series of exciting lectures. My name is Dr. Elik, and today we'll begin by looking at proteins and amino acids, concentrating on amino acids as biological macromolecules of proteins. So we'll just get started with that. So we are looking at amino acid, and we say that of the biological macromolecules, proteins are the most abundant. They are the workforce of the physiological system. That's very, very key of biological macromolecules. So I'd like to state that down of the biological macro. So of the biological macromolecules, supposed to be an M here. So sorry, I just have to write that again. Of the biological macro biological macromolecules, we say that proteins are the most abundant. Proteins are proteins are the most abundant. They are actually the workforce. They are the workforce They are the workforce of physiological systems. They are the workforce of physiological system. Workforce of physiological systems. Yes, this is very key about biological macromolecules. We have several biological macromolecules, and we say that proteins are the most abundant. They are diverse. They are everywhere. Another important thing to note is that proteins are made up of 20 amino acids. Proteins are made up of proteins are made up of are made up of 20 amino acids. So there are 20 common amino acids. Of course, amino acids are actually more than 20, but we are looking at the common amino acids. They are 20 in number. Okay, so very important. We put the common. There are 20 common amino acids. Alright, so 20 common amino acids. Please take note of the common. And the amino acids, they have a general structure. They follow the general structure. So let me do the amino acids in blue. Excuse me. So amino acids, they follow this general uh, formula representation. Okay, C attached to a double bond, O minus, and of course you have the amino group NH3 plus. Okay, and of course the arrow group, which is the side chain. Now this carbon that is bonded to the four substituents is actually referred to as the alpha carbon. So this is referred to as the alpha carbon. So this is a general and formula representation of the amino uh, um, uh, acids. And it is called, that alpha carbon is called the alpha carbon because it is the carbon that is attached to the carbonyl carbon. So we have the carbonyl carbon right here. This is the carbonyl carbon right here. So you see that this alpha carbon is bonded directly to the carbonyl group. Okay, so that's why it is called the alpha carbon. The only thing that is different from one amino acid from the other is the arrow group. So the all amino acids will generally follow this general formula. So let me just state it here. General formula for amino acids. Formula for amino acids. So all amino acids, like I said, we generally follow this formula. And the only thing that is different is actually this arrow group. What becomes of this arrow group, or what is attached as the arrow group, is what actually differentiates one amino acid from the other. So you also noticed that there are four different groups that are attached to the alpha carbon. So the alpha carbon that is right here in the middle here, this alpha carbon here, is attached to four different groups. So we have seen the carbonyl group, which is this, the arrow side chain. Then of course you have here the amino group attached here, and the hydrogen. So it is attached to four different groups or substituents. So as such, this alpha carbon can be called a chiral center. So again, this alpha carbon can be called a chiral center. Majorly because it is bonded or attached to four different groups. So each amino acid that we'll see as we begin to look at it, except for glycine, exists as what? An enantiomer. So I'll take that in the next page. Each amino acid exists as what? Enantiomer. So we'll write here. So each amino acid, like we see previously. So let me just quickly redraw. So we have this is bonded to an H, this is bonded to an R group, and this is bonded to an amino group. Okay, so we said it has four substituents. This is referred to as what? the alpha carbon, and we said that it is called the alpha carbon because it is bonded to the carbonyl group, which is right here. This is the carbonyl group right here. Okay, so now we are saying that this arrow group is what differentiates one amino acid from the other. So as a result of these 4 different substituents or group attached to the alpha carbon, what we have is that each amino acid will have to exist as an enantiomer, except for glycine, and you will know shortly why that is. So each amino acid except for glycine except glycine exists as what? Exists as an enantiomer. They exist as an enantiomer. So, or they exist as an enantiomeric pair. Alright, so if I have a solution of alanine, for example, and I have not separated that solution into its left-handed or right-handed alanine, if I pass some plain polarized light through the solution, one of them is going to be rotating to the left and the other will rotate to the right. So an atomeric pair in which amino acid exists in are actually existing as what? Either left-handed or right-handed. They are actually existing as either left-handed or right-handed. So depending on where their rotation goes in solution when a plain polarized light is passed through it. So all of this has to do with how these groups are arranged in space. So remember that enantiomers are mirror images. So you could be asking, what's enantiomer or enantiomeric pairs? They are mirror images that are non-superimposable. Just as the right hand and the left hand cannot match equally when placed on each other, they are not superimposable. So if you are not clear with this, you really need to revise your organic chemistry. So amino acids generally, they exist as what? Enantiomers. Alright, so configuration in biochemistry is based, so based on this we actually are able to what? Name amino acids. And configuration in biochemistry are actually, let me do this in a different color. Orange. Alright, so we say configurations in biochemistry. Configurations in biochemistry are or is based on the DL system. Is based on the DL system. So it's based on the DL system. And the reference molecule that is used in this type of DL system configuration is actually glyceraldehyde. So the reference molecule against which the configuration of other molecules is decided is what? Glyceraldehyde. Glyceraldehyde. And you will know shortly why that is chosen. So it's just a convention that is just chosen. So in our next page, we'll be talking a little more glyceraldehyde. Now, let's look at glyceraldehyde. We want to look at the structure of glyceraldehyde. So we'll take a look at drawing L-glyceraldehyde. So alright, so this is L-glyceraldehyde. Alright, and this presentation is actually what is represented or known as what? The Fisher's projection. Alright, and is actually equivalent to this presentation. So we have C. This is how it is normally presented. So we have CH2OH, and we have this don't know why my pen is not cooperating as expected. So the alpha carbon, which is, as you can see, just like what we saw with the general structure of glyceraldehyde, the alpha carbon is at the plane of the page. So when I hold a molecule in space, remember that carbon is what? A tetravalent group. That means it has 4 groups. So we are looking at this also, just like we saw in the amino acid group. This also is the alpha carbon. Alright, so when I hold a plane, I hold a molecule in space. The alpha carbon, which is tetravalent, that means 4 groups is attached to it. They are arranged on it in a tetrahedral arrangement, which is what is being shown here outside the Fisher's projection, trying to show you the tetrahedral arrangement. Alright, so that's they are not just one arranged on top of the other. So but it is a planar molecule, like a 3-dimensional molecule. Once the carbon is held like that, the hydrogen and the OH actually comes out towards me, that is the one holding it. So that's equivalent implies that it is going to, so this wedge, the wedge that is shown here, the wedge here, this wedge actually shows that it is going towards me. So that's the OH and the H, and this dash shows it is going away from me. So that's how you know it. So this on the vertical planar implies it is going away from you, and this on the horizontal planar implies it is coming towards you, and it is indicated by the wedge. Sorry, my wedge is not properly drawn. So it shows that it is going. Okay, so that's it. It's going towards you. So they come out from the plane of the page towards me. The Fisher's projection is just a line, like you can see here. The Fisher's projection is just a line, just like you can see in this whole structure, and it's representing, and all of this represents the equivalent of the Fisher's projection, which is the line projection. Anything on the vertical, like I said earlier, anything on the vertical axis means that they are pointing away from you, while this OH and H on the horizontal are pointing towards you. Alright, so with the this is for L-glyceraldehyde. So let's just quickly now look at what the D-glyceraldehydes look like, since we said it is based on the DL system. So the D-glyceraldehyde is now something like this. Okay, so this is the D-glyceraldehyde. So that is D-glyceraldehyde. And again, if we draw its equivalent representation, what we'll have is something like this. So when it's going away from you, which is your vertical axis, what you have is a representation like this, and so this is CH2OH. Now this is actually a wedge. So I'll just do that again. So this is okay. So this is like a wedge. Then you have your OH here and another wedge. Right? I think this was done. So you have your OH here. So that is the representation. So notice that the only thing that is changing between the L-glyceraldehyde and the D-glyceraldehyde is the H and the OH substituents. So you reverse the orientation, changing L to D and changing D to L. So the only thing changing is that in your L system, your OH is on the left of the alpha carbon, and in your D system, your OH is on the right. So changing it from the orientation from left to right automatically changes from D to L and vice versa. Note that all amino acids in biological proteins are the L enantiomer. So we'll begin that in the next page. So we say that all amino acids in biological protein, the representative of of the glyceraldehyde molecule. All amino acids in biological proteins are the L-enantiomer, so their configuration matches what the L-glyceraldehyde, like we saw and talked about. So when we talk about amino acids, we are actually talking about L-amino acids, and we are actually in specificity referring to what the L-amino acids. So we'll quickly now look at the structure of the L-glyceraldehydes in comparison with the L-amino acids. So just for the note, for you to note down, let me do this in orange. We said that all notes all amino acids in biological systems are what? Are the L-enantiomers. Are the L-enantiomers. Are the L-enantiomers. So their configuration as such, their configuration matches the what? L-glyceraldehyde, like we saw earlier. The configuration matches the L-glyceraldehyde, like we saw earlier. So when we are talking about amino acids in general, we are actually referring to L-amino acids, and specifically L-amino acids, and specifically we are referring to what? The alpha L-amino acids. So we want to quickly now look at the structures of the amino acids and glyceraldehyde side by side. So I'll do this in red. So if I look at let's take the structure of glyceraldehyde again. So we have the alpha carbon bonding to carbonyl group, so we'll be at this point we are looking at the L-glyceraldehyde. Alright, so what we have here is a what? Alpha carbon, and what we have here is what? Your L-glyceraldehyde. So L-glyceraldehyde. Now, if we look at it side by side, your amino acids again. So we have the alpha carbon for amino acids bonded to the what? Carboxylic group. It's bonded to the carboxylic group. And you have the arrow group. Then you have the amino group. So this is the amino group. So again, this is what? The what? Alpha carbon. Alright, so here in this structure here. Sorry. So if in this structure here you have what you call the carbonyl carbon, carbonyl C, and is also represented here. Then here you have the hydroxy group. You see, they are all bonded to different subsequent, showing that they are enantiomeric pair. So here you have the hydroxy group, which is your OH group, your hydroxy group, the hydroxy group. Alright, of course, then you have the this another group here. Okay, so now in this one you also see such similarity. Here you have the carbon again, carbonyl C. Of course, the alpha carbon is there, and here you have the amino group. You have the amino group, showing they are all in an enantiomeric pair. You have here as the amino group. Then you have this arrow side chain, and of course the H. So you see, this is bonded to 4 different substituents, making it an enantiomeric pair, and making the alpha carbon a chiral center. Same thing with the amino group. So this is why the glyceraldehyde, the L-glyceraldehyde, this is actually L-amino acid. L-amino acid. So this is why the L-glyceraldehyde is the reference molecule for the configuration of amino acid. This is how all amino acids in your body will look like, and we could as well draw the equivalence showing this. So if we draw the equivalent like we saw previously of the amino acid, what you have is this whole planar represents the vertical in plane polarized light. So you have your C, your double bond O minus, and of course this down here is the planar, represents your R. Why this horizontal planar is represented by the wedge that is coming towards you, the wedge that is coming towards you. Sorry about that. Okay, so this is your NH3 plus, and this is your H plus. So H plus is represented by this wedge coming towards you in the horizontal, while in the vertical is represented by this dash going away from you. So basically this is how all the amino acids in the body looks like. So we continue. Just so you know, L-amino acids correspond to the S enantiomer in the ROS system. That's studying your stereochemistry.